Thanks for the invitation and introduction. Um, let's start by telling you what our platform is, and then I walk you toward our experiments we have done on this platform. The platform that we have chosen and we are focusing on is based on Josephson junctions. So they're called superconducting qubits. And the physics of Josephson junction is about a half a century old, meaning that about a half a century ago, Josephson realized that if you have two superconducting islands and you bring them very close to each other, Cooper pair can coherently tunnel from one to another. And this is how we make them this day and age in the lab. You deposit a layer of aluminum, a little of aluminum. This is maybe 200 nanometer in width, and then you oxidize uh, the chamber. You put oxygen in there. The aluminum oxidizes, so there would be a layer of oxygen formed, hard to see in here. And then you deposit another layer of aluminum. So you deposit two aluminum on top of each other, and what is not aluminum, like where the mouse is maybe silicon or some totally insulator. So Cooper pairs tunnel through this layer and they form a Josephson junction, which the current and voltage obeys this relation. And the beauty of this two relation is you essentially are realizing a nonlinear inductor, meaning that the phase difference across the two across the two islands, this is the Ginzburg-Landau superconducting phase, would set the current for you, the current that you're getting in there. So basically, it's a very nonlinear element, and you can put an array of them together. In this case, what you're seeing in here is a Josephson junction followed by it's shunted by a capacitor, and you have 9 capacitors in this example I'm highlighting, and they make 9 qubits. I call them qubits because there are many layers in them, there are many energy levels in them, sorry. But the level of spacing is non-uniform. So you can only manage to focus on these two lowest levels. And essentially you can realize a giant atom. By that I mean that you can control the level of spacing by changing the geometries that you have. This size of this junction sets the current critical current sets the inductance, and the size of the capacitance in here sets the essentially sets the level of spacing. So you have full control over this geometry, and it's all coming from someone sitting behind a computer and drawing geometrical objects. So this is a chip made of aluminum deposited on silicon or sapphire, and the colors you see here are just to guide the functionality of each element. There is no it's all aluminum. There is no color to them. And then you have readout resonators in here. The readout resonators would allow you to read the states of the qubit, but note that there's 2 wires coming and going, meaning that all the qubits can be read at the same time. Each of these lambda over 4 resonators you see up here has a slightly different frequency. And there's a Stark shift which is set by if this adjacent qubit is occupied or not, and the associated resonance frequency of this resonator shifts a little bit, and based on that you can figure out if the associated qubit was occupied or not. And you can see we have lots of wires coming in, and they would use to control the degree of the freedom of the qubits. So in what we have realized and what we have synthesized in here is the negative Hubbard, attractive Hubbard U Bose-Hubbard Hamiltonian. So we can excite a couple of qubits, and you let the excitations go around, they would obey the Bose-Hubbard Hamiltonian. And these are the range of the parameters you can set with your voltages and currents that you send to these lines. This would be one way of dealing with this system. Another way is to turn on and off these coupling terms and the individual on-site potentials, such that you have generate gates, unitary operations that are textbook operations that you see in a textbook. So this would be the way we chose, but I'm telling you that just studying the free dynamic of photons in a Bose-Hubbard Hamiltonian is also an option. So this is a picture of our team about a few years ago when we did the quantum supremacy beyond classical experiment. And basically in this experiment, we took a processor with a much bigger version of this processor I'm showing in here. And now we are going to 2D geometry, and we are putting 53 qubits together, 54 qubits. One of them didn't function. I'm showing you the schematic layout of the qubits. So you can put them in a 2D grid and you can pulse it as I'm showing you here. These are the schematic of the pulses we can apply. And you can start from a very simple product state, and very quickly you can create a highly entangled state. And from this resulting wave function, you can sample rather quickly with our processor. You can get 10,000 bit strings or maybe 100,000 bit string per second. You can generate this, you can destroy this circuit, you can let it go back, and you can repeat this experiment maybe with about 10 kilohertz frequency. You can repeat the experiment, and this become crucial for the later part of the talk, that with the fact that we can really sample fast. So, but there in
I
this
ask you maybe just a question just to understand
please,
a little
please.
bit the basics. So maybe if you go to the slide where you still have the Josephson junction. Yeah. So how many levels do you have good control over, like from 0 to many? I guess that's the boson occupation, right, of each.
Yeah, that's a very good question. We don't even go there. We don't even go there. I think if you put, let's say, 5 photons, there is a chance that they go, I mean, like they obey these equations, and going from one level to another takes time, but eventually they go to those levels. But the fact that our readout is not capable to read them, we never push that limit.
Mm-hmm. So you're only working with 0 and 1, basically?
Not exactly. We usually rely on dispersion shift. We usually rely on dispersive shift that comes from the second layer. The occupation at the end of the cycle, you have to where you find your excitation is either 0 or 1. This is either there is no excitation or there is 1. But there is a dispersive shift without the population, without the photon going in there, that it is required for the correct modeling of the system. But sometimes if you have a good platform, like Erfan Siddiqui's group really use this level because they can read it out. So they do qubit physics for real. For us, because we want to do qubit physics, we call this leakage, and we consider this as error.
I see. Okay, thank you.
Sure. So so these are a bunch of single qubit and 2 qubit unitary operations you can do, and you can sample. But you can see that the problem that I'm describing is a well-posed problem, but is a bit contrived problem. We created to outperform a classical computer by doing a problem that we know, of course, we have advantage, and may not be a very practical problem. So what kind of interesting problems can we do? This is a very approximate map of the problems that one could do without error correction. One school of thoughts, of course, is that you make qubits which are 10 to the minus 3 in terms of error rate. 2 qubit case are on that regime. And then you make lots of them to realize a logical qubit. But another idea which was mentioned in the introduction was that you don't make that many qubits, you just make a few tens of qubits. And then you make them qubits better and better. there is a chance that you can solve these problems that are very close to the heart of physicists and chemists faster than a classical computer. But you need really good qubits. You don't need that many of them. You need a very good ones. And then you can see that chemistry and fermionic based problems are a little harder than, of course, than basically spin problems, non-equilibrium dynamic problem, because our excitations are bosonic, so you need a Jordan-Wigner transformation, which is going to be costly for you. So it's not accidental that the experiments we do usually falls into this category. From the works that we have done and published recently, I'm going to choose two of them and describe to you what they are about, and hopefully it resonates with you. The first work is about a year or so old, and this is done by Google collaboration, but these colleagues of mine put more energy into them. And the story is about formation of bound state of photons, microwave photons. So there are a couple of terms that I want to clarify, and I will discuss during this part. So one is bound state. What do I mean by bound state? So you should understand what I mean by that. You can see clearly it's been discussed since ancient Greek time that what is actually it is. And what do I mean by photons? And also, at the end of the day, we are going to break the mechanism which led to these bound states and see what is the resilience of this bound state to this perturbation. The idea of bound states and integrability and whatnot of XXZ Hamiltonian goes about a century old. So Heisenberg, about 100 years ago, he wrote this Hamiltonian, which is actually make very much sense to study magnetism in one dimension. And then not long after, Hans Bethe was able to use the method now we call beta ansatz to show integrability of this method. So essentially bound states and it shows that this model is integrable and whatnot. So if a model is integrable, then you can hope that there is a bound state and you can find them, which is what Thomas Fabian Essler and his team figured out. And then a year later, Emanuel Bloch and his team, they actually realized bound states in this model. So what do I mean by that? It means that if you have a chain of spins, if you create these initial states, meaning that, or in one language, you can call it two magnons. If they're bound together, every later instance of time that you come and take a look, they are together. You just see them, they are together. There will be a superposition of all possible states, and all these states are together. But if they're not together, if there are no bound states, you can find them separately. And the point of the work of Emanuel Bloch and his team was that every time they observe it, they seem together, and they look at the speed of propagation of them, and there's a chance that they get broken, and they study this physics very carefully. So I like this problem because now we can cheat and we can do something in our platform, and there's a very good base for comparison between various quantum simulation processes, and we can essentially grow a unified language eventually to talk about how quantum processes should be used to do quantum simulation. We are not doing exactly the same problem. We are doing the Floquet version of it. So in this rest of this talk, I'm going to show you things which look like this. This is a 2-qubit unitary gate, which we call it fermionic simulation gate. It's a historic name, and has this in the 00100111 basis appears in this form, meaning that there is a hopping term which takes 01 to 10 with the size of sine of theta. And there's an interaction term, so you can see there's corresponding to these terms in the Hamiltonian version. If theta and phi were very small, you're essentially dealing with a Trotter expansion of the Hamiltonian. But we are not going to keep them small, we are going to keep them large, because the same physics follows, and you don't need to be on the Trotter expansion of the Hamiltonian. The properties I mentioned has been proven to exist for the Floquet dynamic too. There is a work by Thomas Prosen and his team, which shows that the Floquet version, meaning that you apply the sequence of these gates where theta and phi are not small, this is integrable, and followed by a work by Igor Aliner, which shows that there is bound states and he can write analytical forms for the bound states. Beta is the phase that you can accumulate during complex hop. The hopping could be a complex number, and it become relevant later on. So why should you be excited about it? Or why should bound state excite anybody? It's an interesting physics. You see, you have excitation, let's say in a semiconductor solid state setting. This excitation's lifetime usually is set or is sizable because the excitation exists in the gap of a semiconductor. There's no energy in its vicinity to decay into. Here we are talking about bound states that their energy overlap with a continuum. So we are dealing with Floquet. I'm showing you the eigenstates quasi-energy of the problem on a unit circle, and I'm showing you that there is a continuum of energy levels, and my bound states overlaps with them, yet it does not decay into them. And that is the beauty of the physics and the prediction, and it's happening because you have extensive number of constant integrals of motion that the system is integrable. So what do I mean by bound state? Let's say I go back to our Sycamore chip and I chose 24 qubits and I put them, and I can choose which qubits to use and which qubits to turn off, so I can carve out a closed loop of 24 qubits. Now, if I excite few excitations, few qubits in the middle in here, and I look at later instance of time, every time I come and take a look, I see a bit string. I see a single bit string. But these bit strings are such that the excitations come together. So I'm going to conclude I have a superposition of all these bit strings with some complex numbers, which is not easy to read at the moment. So this is what we are going to do to prove, at least partially, that we have bound states. So
Could I ask you a little bit about the model?
Yeah, yeah, please.
Sorry, this might be very naive questions, but just to learn a bit. So is there any point in which this will map into some kind of free fermions, free Floquet fermions? So like for the usual XXC, you know, when delta equals 0, you have free fermions, basically.
Yeah.
Is there any case of like
I would say so. I would say so. If you make phi in our case 0, I think probably yes, you're right. I think this will be free fermion. I think so. But so that's a good point. I can add that Igor's work shows that phi has to be at least 2 theta to have the bound state.
I see.
So we're gonna
so phi is a little bit like delta in the.
Exactly.
I see. Yeah. I see. Very nice. Okay, good.
Well, later it become clear, but you can take my words for now. Okay. Sine of phi. Let me get this straight. Sine of phi over sine of theta or sine of theta over 2 is delta. This ratio of sine of phi to sine of theta, and I'm missing a factor of 2 somewhere, is delta.
I see.
On the second part, it become relevant.
Okay.
So, sure. So we have 24 qubits. Qubit 24 is next to qubit 1. And I'm going to put one excitation here because just as we discussed, we're just going to kill this interaction physics. Is a one excitation. There's nothing for it to interact with. And as a function of time, we're just going to run once Floquet circle, make 10,000 measurement, 2 Floquet circle, 10,000 measurement, start over again and keep going. And then I show you with color where I find the excitation. This is the probability of finding the excitation. I have 10,000 measurements at each depth, so it's easy to form probabilities. You can see a pattern of a random walk, very healthy cat walking or whatever on this 1D object, and is a single qubit, single excitation random walk. There is no interaction. But then when you put 2 excitations, I can repeat the experiment, ask where is my excitation, what bit string I get, and here is the intensity of the bit strings, where my bit string shows 0, where my bit string show 1. I average everything I get. This is the pattern. You can see it seems that the front moves slowly, and there's a concentration getting toward this energy, toward this propagation. But then sometimes you see a shadow of the old pattern too. You repeat the experiment with 3 excitation next to each other as initial state, and 4 and 5. By the time you get to 5, you see there's lots of bit strings show excitation close to origin. Okay, this is indicating that when you have 5 photons, it seems they don't want to go anywhere, and you find your photons, your excitations, your ones close to where they have started. Let me do a little further analysis of the same data. Bit strings that we get, let's say for the case of four excitations, either the excitations are together or they are not together. They can be separated into these exclusive categories. And I'm just going to trash for the time being all the bit strings that fall into these buckets. And I'm just saying, let's just focus and chase the cases that the bit strings are together. Since they are together, I don't need to highlight 4 pixels. I highlight 1 pixel. I call it center of the mass pixel. And if I go and analyze the same data again, you see a pattern which very much looks like the single excitation with just a slower velocity. What I'm going to conclude from this is that now these 2 excitations are happily moving together and creating an interference pattern which is very similar to the single excitation. So they're bound together and they're walking together, and this dynamic become visible as soon as I did my arbitrary filter applied in here. And you do 3 excitations and whatnot, you see slower propagation, and 4 and 5, the pattern is the same. So it's just the 5 bit strings are together, they did not move much. How much they should have moved, the envelope that you see in here can be extracted and compared with analytical results. And you see that it goes rapidly fast. It gets heavier and heavier. The bound state's mass essentially gets heavier, so it travels, propagates slower. So how bad was this filtering? Should I filter? Should I not filter? What was that? What was that about? I'm plotting the ratio of the bit strings that are together to the total number of bit strings I get. Okay, this is the if they were always stay together, if as good as the numerical results, these lines would have been flat, meaning that there is some initial whatever interference and breaking and whatnot, but then after that they are always flat. The ratio of the bit strings that are together to total bit strings I observe, we should not change. Our system is an open quantum system. Unfortunately, there is different the coherence and the phasing, and the bit strings break, and that's the rate they break. But after I clean the physics, I can see the physics. Okay. This is about the real space picture. I want to go and show you stuff about the momentum space picture. And I want to please the condensed matter theorists, or maybe someone who has done ARPS experiment, and show our case of how well we can do band structure. So I need to introduce you a technique that we use. This technique is not scalable, but is good to show you some basic physics in here. I get panic for a second about my charger. Let me just go out. It's all good. Okay, it's charging. Okay. Okay, so you guys should see the screen again and everything should be fine.
Yeah, everything good. So Pedram, just to understand
yes.
something you said. So if you were simulating this exact model, this Floquet model, exactly, what you were trying to say is that these curves should eventually saturate to some constant?
Yeah, like after this initial finite size, whatever, something about the eigenstates not being exactly these states. After this, from let's say cycle 10 or 20, these lines should have been flat. Should not go down after that. Yeah. Then there should not be breaking. The initial thing is coming from that. Yeah, there are a couple of eigenstates are involved in forming your initial states, and they do little interference among each other initially, and after that, there should not be any change in this ratio. Okay, so I want to do a little physics 101 on how can we do band structure and how do we momentum resolve physics. So I'm going to switch for the sake of simplicity to Hamiltonian system. Let's say I have a Hamiltonian H which has eigenvalues, eigenstates phi with eigenenergies omega. If I create an initial state without thinking much, this initial state of overlap can be decomposed into eigen states of the Hamiltonian, and the evolution of it is set by the Schrödinger equation and can be written in terms of these eigenstates of the problem. So miraculously, if I could get the overlap of this initial state and psi of t, something that theorists probably think can do a lot, you get a complex number. This is a complex number as a function of time. You have a real and imaginary part, and this number is just going to be changing in time. But look at it. If you do a Fourier transform of this, you get all the eigenenergies of the problem back. So that's a beautiful object to construct. But the question is how. So I tell you two recipes, and you can generalize it for yourself, that this overlap, it can be synthesized in the lab. I'm showing you a unitary e to the I ht in this case of the same Hamilton of a Hamiltonian, which is photon preserving. And let's say I put one qubit on the equator and I create this initial state, and I measure a lowering operator. So this is a green function, this is a lowering operator, so maybe the physics now will become very clear to some of you. This is a non-Hermitian operator, so you have to measure x, and then you have to repeat the experiment, measure y. You add them with this prefactor, and you make the expectation value of this observable, given that that was your initial state. Under these two conditions, the result of this expectation value is exactly this green function that I'm showing in here, and can be Fourier transformed. The method can be extended to few excitations. This is the case of two excitations. You put two qubits on equator. You measure the lowering operator in any two qubits. In this case, I chose them to be the same. And the lowering operator is made of four parts, which they have to be all done independently, and then bring them together and add them up. So 4 experiments to do this. And the Fourier transform of this object is exactly the 2-photon spectrum that you're after. And this is the generalized formula. You have to create initial states of a given form, and you have to measure Pauli strings. So if you want to do 5 photons, which we are showing, 5 photons would take 32 configurations of measurements, and each of them has Pauli strings, which are 5 strings long. They have support in 5 lattice sites, 5 qubit sites. So it's very unscalable, but we did it. So let me show you how data looks like if you follow this procedure. You have to measure this. I don't know why it's becoming a raising operator, but anyways, physics is not that different. You measure these operators. I'm showing you the real part of it, an imaginary part of it. So it comes from measurements that are added together. It doesn't come in a single shot. You make these complex numbers, and it looks like nothing, right? You Fourier transform this by 2D Fourier transform. And the space maps into time, and the space map into momentum, and time map into energy, and you see a very good-looking dispersion relation as E versus K. I mean, in the floated basis, and you can continue this procedure. It gets very time-consuming, but you can nevertheless do it if you have the patience, and resolve the band of these bound states up to 5, the band that's composed of 5 excitations. And the dashed line is the theoretical prediction by Igor Aliner, which we put on top, and more or less there is a good agreement in there. This is all good. This is all reasonable.
So just to understand a bit, so you're saying basically that you can measure like 1 body, 2 body, 3 body, 4 body, 5 body Green's functions?
Yes.
Is that So this is a single system, but you're changing the operator that you're measuring.
What do you mean single system?
You know,
Unitary is the same.
no,
In the
no.
Bose,
Yeah, in a given chain, I could measure the one-body Green's function.
yeah.
Or I could measure the two-body Green's function.
Yeah, but two-body
sort of
Green function is totally different sector of the Bose-Hubbard Hamiltonian, right? It's not, these dynamics are, maybe that's not important. But yeah, we can measure that. But the dynamic is photon conserving. So when we put 5 excitation, we are in the sector of the Bose-Hubbard Hamiltonian, which has nothing to do with the other sector. So
I see. This label is the initial number of photons that you had when you started propagating.
Yeah, but that number, because the dynamic is photon conserving, confines the dynamic to a photon conserving sector.
Right.
So these
so these Green's functions are measured for different initial states, let's say, with different total number of photons, but you still measure the sort of n-body Green's function for each.
N-body Green function, the relevance n-body Green function in each case can be measured. But this is 2 choose n, right? 3 from n, 4 from n is not 2 to the n physics.
Right.
The whole Hilbert space is not available because we are going to do dynamic in their photon conserving sectors.
Right.
Yeah, but what we can do, wait, now it's about to get really beautiful. Listen here. So this beta thing that I've been trying to sell to you guys so far, now I'm going to bring it back in here. This beta means that a photon that hops can gain a complex, the hopping value can be a complex. And when I have a closed chain, this cannot be gauge transformed out. So this is a physical quantity, is a flux thread going through the loop. The flux value is the sum of all the complex hoppings that the excitation can get upon individual hopping. And so what I'm doing is I'm doing my ARPES equivalent, if you want to think about that, the ARPES of a 1D ring, while I'm changing the flux magnetic field penetrating through the loop formed by this ring. And the band that it was formed now is very nicely start to shift and slide in front of your eyes. And that's the beauty of it. You can use the rate that the band shifts as in energy versus K to talk about, to extract the pseudo charge of the band of the charge of the particles that this band is composed of. And you can go all the way to 5 excitations. So we got the mass of them. You saw how sluggish they got as they get heavier. And now you can extract the charge of them. It's a very intense thing for our system. It was because of noise and all this physics. It took many hours. You can get it. It's very rewarding, but at the end of the day, the answer is very boring too. So when you have 5 excitations, the charge is 5 and so on. So we can extract it, but also you get something boring at the end too. So we get the band, we look at the effective mass, effective charge, everything is under our control, and now we can get to. Yeah.
This is very cool. So maybe if I can ask you.
Sure.
So just to understand, so this flux is static, right? So you're repeating the experiment for each different flux?
Exactly.
Is it possible for you to do it like dynamical, the flux?
Yes, we can. Yes.
Oh, that's really cool.
Yes.
So you can do like, shining light, right? Because if you make the flux dynamical, you could simulate like an AC electric field on the chain.
You're right. It didn't occur to me. You're right.
Yeah, that's really cool. So you could do
what you're suggesting is that in one layer of this dynamic, use one value of beta, in another layer of the dynamic, in the next cycle, choose another value of beta.
Right. Time is discrete in a sense for you. Yeah.
Yeah, it's super easy.
Right.
Okay. So, well, maybe I don't say too much about in here. Sorry, this is an unfinished slide for summer school. The integrability, maybe I'm talking to experts in the room only for a minute. And the integrability was proven by Yang-Baxter relation, which shows that when you look from far, the order of the scattering of three particles does not matter. If one hits two and then three versus two and three hit each other and then hit one. So, but the integrable models are very fine-tuned models that, because we want to build intuition, analytical methods and theoretical physics is usually evolve under them, but they are in a sense not realistic because they are fine-tuned. And there would be a very vulnerable point for theorists that we of course love to attack, because they have been fine-tuned something which is maybe not very realistic. So it's an Achilles heel, but it's the other way around. You know, Achilles was for the most part not vulnerable, and only has a very tiny part. But this, the part that is not vulnerable is integrable system, is these very fine-tuned integrable cases which form a set of measure zero, in fact, in the sea of integrable systems, in interacting systems, sorry. So anything you do pretty much breaks integrability, and we're gonna seek joy in doing so. So let's just go ahead and do it. The way we chose integrability breaking is by going to 2-dimension or quasi 2-dimension. You make a chain of 14 qubits, and then you're going to introduce 7 extra qubits, and you're going to tune the coupling to these extra qubits. And as you do that from the Hilbert space, so now you see the Hilbert space 3 of 20, which was original one, now, sorry, 14, you go to 321, and your Hilbert space gets 4 times bigger. And you're going to change this theta prime parameter, which couples you to this external dimension. Okay, so I have been showing you the bands, right? We get the bands figured out together. So this, and I'm showing you the schematic findings. This is the 3 excitation band, which overlaps with other continuum bands. When they break, they would be overlapped. There is an energy for them to go to in the nearby part of the spectrum. So a simple argument based on the Fermi golden rule tells you that as soon as you break integrability, these T-bit strings go to S-bit strings, and the bound states would go away very quickly. So that was our intuition when we started this program. Lo and behold, we are about to find something rather interesting. On the vertical axis in here, we are showing the chances of bound states staying put together, the same parameter I showed before. If there is no perturbation, this is the rate. So this is ideal case in our case, that the bound states are together for all at all time. If you make a very strong perturbation, this theta prime is the angle connects you to the dimension outside one dimension. You do very strong, boom, everything breaks, and you have no bound state, and the bound state quickly goes away. But you have sizable perturbation as big as theta prime is pi over 6. And you can see the behavior is closer to the absence of integrability breaking. So that's a surprising result. We got more data, which very slowly we change this parameter, and you see that very slowly these are going to the other one rather than sharply drawing it. Let me show you a cut or 2 cuts through the same data. This is the physics, the same data, sorry. I'm showing you the cut in here. For early cycles, for up to very sizable perturbation, that's the theta prime angle. For very sizable perturbations, the bound states are staying together. This part is rather flat. And only very strong perturbation, they start to break and whatnot. That is a rather surprising finding. We can see the same physics, the same discovery, the same observation in the band structure picture, in the momentum space picture. You have a band formed by 3 excitations, and then you increase the perturbation all the way to the perturbation value in which the band is fully gone. So what is this peak width? So some notion of peak width divided by, I don't know why it's not normalized, but anyways. So this is showing you measure the strength of how they stay together. Again, based on a Fermi golden rule, you probably guess that boom, it would go away very quickly. But we find that no, indeed, they are staying together for a very sizable perturbation. So I like to call it a discovery, not because it was beyond classical or anything. It's just mainly because it was unexpected, and the quantum processor came across it for the first time. And this is far beyond the perturbation limit, far beyond the comfortable physics of pre-thermalization. And so still a good explanation for this is missing. And there is no CAM theorem for quantum systems, so we even don't know what to expect for perturbation in a quantum system. So the finding of us later was confirmed by Dima. Again, this was a small problem, so Dima could do a very extensive numerical set, and he can, with a level of statistic, first you can see that you have break in the integrability, and you don't you have a very good level repulsion in the system, so they follow COE distribution. That's very good. And also he can show that this overlaps. Well, he's doing some other measurement, but these overlaps are rather fixed, and as a function of time for various sizes, and with some truncation method, he could go to very, very large systems. So everything we are finding, at least in the limits, we are seeing this resilience has been repeated numerically, but the point is that the numerical happened after we have done the experiment. Okay, I want to, in the last 15 minutes or so, I want to cover this experiment, if you don't mind, if we have time and no questions.
Please go ahead. So actually, maybe if I could ask you, it's okay if we run over time a few minutes.
Okay.
So, but the idea is the integrability breaking makes the bound states decay, right? So
what I'm saying, naive thinking says that. Naive thinking based on the Fermi golden rule, well, it was unexpected. Of course, if you figure out exactly what goes to Fermi golden rule and all that, and probably it's all fine again. Well, but the resilience they show to integrability breaking is far beyond what perturbation suggests.
Right. Right.
Yeah.
And so, how do you kind of tell apart, that this is, I guess now there are the simulations, so that might help, but how do you tell apart that this is, sort of an ideal behavior of the breaking of the integrability of the model versus some other issues of the system not being completely, closed and, having decoherence and all?
No, we don't. You're right. You're right. That's why we asked Dima to do this level repulsion physics. Yeah, you're right. There was no way for us to know. We find good evidence, and we want to make a big fuss about it, and then we asked Dima to check for us. Yeah. Otherwise, yeah, it would be only a speculation. Well, yeah.
Okay. Very good. Thank you.
Sure. So the next physics is based on a rather recent post on arXiv, early part of this month, is done by this group of people mainly, and goes to this community conjecture that you may heard about it, that a spin dynamic in a Heisenberg chain follows the Kardar-Parisi-Zhang universality class. So I'm about to describe to you what this conjecture is about, and then we see what evidence we are finding for it. Well, let me tell you what we have measured. Let me tell you what the spin dynamics they specifically have in mind. In an open chain of qubits, in this case, we are dealing with 46. This is the equation I promised you, and I think I said a factor of 2 wrong. The conjecture is for the Heisenberg Hamiltonian, or the same thing. You need SU2 symmetry, so you can just work with the unitary case, with the Floquet case, with as long as you get this ratio of phi and theta correct, so delta become 1. You want delta become 1, so XXC become Heisenberg. You get this ratio to become 1, then you're doing the same physics as far as this problem is concerned. So in a chain of qubits, 46 qubits in this case, you excite the qubits on the left. Let's say you put them on one state by this probability, and with the minus of that probability, or 1 minus that probability. So you put those qubits down. So I notice I'm using the same thing, but one is probability of being blue, one is the probability of being yellow. So let's say mu is infinite. Everything on the left is blue and everything on the right is whatever, golden or yellow. And you create this initial state, and then you let it evolve under this unitary, and you ask a simple question: how many excitations, how many blues cross the middle? Since every blue has to cross, a yellow has to go the other way, is the same question. You can ask either of the same two questions. And you repeat the experiment for each cycle 10,000 times or so, and you form a histogram. And I'm showing you the evolution of this probability distribution as the absolute unit of counts that we get, and there's a post-selection and the excitation goes away, or the normalized probability distribution you've seen here. And what you're seeing here is the number of photons that cross the middle of the chain, or maybe actually, well, it's slightly different, but we're going to get there. So this is more official version of the problem. This is the initial state, and I'm describing, and you choose a value of mu, which shows the contrast in your domain wall initially, and you repeat the experiment for many cycles before you hit the wall. So it was a chain of 46 qubits. We start right at 23 because we didn't want to get the bounce effect from the wall. There was no point of doing that. And I'm showing an instance of a bit string for all these cycles. And we can change the contrast in the domain wall, and the problem become harder and harder. That sets the contrast in the initial state. And we can make a histogram for all these values of mu and for all these, for time and whatnot. And we introduce this stochastic variable m of t, the number of excitations of number of ones in the bit strings, let's say on the right side, minus number of, I don't know what, okay. Number of excitations at initial time. I don't know what one is. Okay, so you have these beautiful probability distributions you can form. It takes many months to get them. But what is the relation to Kardar-Parisi-Zhang equation? This is a classical equation written to describe the growth of interfaces. Is a diffusion equation with the simplest nonlinearity term possibly added in there. And since this nonlinearity is positive, it is diverged quickly. So there is a conjecture which we are not going to prove or disprove. We're just going to take it as face value, which is the called ballistic deposition. If you have, which is the snowfall that more or less you're seeing, and it's very close to the spirit of the Kardar-Parisi-Zhang, but is a simple recipe. You have a chance of getting occupancy or not occupancy coming down. As soon as they see something on the left, on the right, they get stuck. That's the name of the game for ballistic deposition, and is just conjectured to be on the same universality class as the nonlinear equation you see up there. It's just easier to work with. Let's say at time t, I freeze this ballistic deposition. I have a height profile, which I can look at its correlation lengths. I can look at fluctuation in the height, and all these parameters can be extracted. The conjecture says the following. In the KPZ model, if you take the derivative of this height, is analogous, is similar scaling as the profile of magnetization. Okay, it's a bit funny to work with derivatives, so let me integrate for you. If you go to a position, let's say x equals to 0, at time t, and you subtract the asymptotic value of this height, and you define this stochastic variable, this scales the same as this transferred magnetization that we extract together. The conjecture, when formulated, is that these two are the same. There are subtleties into this business, meaning that there is a Kardar-Parisi-Zhang equation and a Kardar-Parisi-Zhang universality classes. These classes depend on your initial state. If the snow or this ballistic deposition Tetris falls on a flat wall, initial state is flat, mu equals to 0, the universality class is different than if the snow deposited on a tilted ceiling. So we're going to be careful with all this, and I'm going to go very systematically through all this physics. Okay, where does the craziness begin? The craziness began from this numerical work, which shows that the KPZ scaling was observed for the 2-point correlation function. This is a numerical work, so they could do all this calculation of the scaling function and whatnot. And for many, many orders of magnitude, they could do this measurement, and they could see in the tail there is deviation from Gaussian, very, very clear deviation. And based on that, they concluded that well, and it also falls onto the KPZ universality class, and based on that, this conjecture is kind of born in the community. Again, there's work for cold atom on this thing, so they do the Heisenberg Hamiltonian, we do the Heisenberg Floquet version, and they did measure this transfer magnetization. They see the super diffusive behavior, which is the signature of one of the signatures, I guess, of the Cardar-Parisi-Zhang universality class. And maybe I speed up a little bit so I can finish in 4 minutes. We could go to the different points, in fact, symmetry point. We can stay at the SU2 symmetry point by setting delta equals to 1. We can go delta less than 1 and more than 1. You probably know that there are lots of predictions for diffusive, super diffusive, and ballistic deposition, ballistic diffusion for the 1D spin chain. So we can study all this physics. And there's no discovery or no thing that was not agreed upon. We didn't find anything interesting that people didn't know before us. But what we could do, we could actually start to lower the contrast in the initial state. And again, the super diffusing scaling is seen in here, and is all fine. We can look into variance of the distributions. I'm showing you the distribution and the numerics and whatnot. We can see the variance also goes super diffusive. That's all good. So we have some agreement with the cold atom experiments which have gone this far. So it's very, very good. But we can go further and we can study higher moments of the distribution. So we are going to skewness and kurtosis of the distribution, and we're going to extract it from our data. It's significant in two senses. In a sense that there was no agreeable and consistent or systematic measurement of them before we did the experiment. And also it opens the discussion that what does it mean to be in a universality class? How many moments of a distribution we have to change? Quantum statistical mechanics really didn't get too much into this question because there was no way of checking it besides numerics. But now that these quantum processors offer a very quick way of measuring these probability, these distributions, you should really think, what does it mean and how many moments have to check? So there's a bit of maybe a slightly philosophical question to think about that. Okay, enough philosophy. Let me show you actual data. So this is the skewness, and as a function of time, but for different values of mu. So when mu is large, the domain will have a sharp contrast, high contrast. Sorry, this value goes from negative, goes up, and probably we would say asymptotically gets into here. And the skewness predicted for KPZ, depending on the origin, the shape of the initial domain, initial state, is one of the two values. So anywhere in between, we should be okay if we land in there. However, if you go to smaller values of mu, where you should go to, you see that the growth is very slowly. So if I say it's not falling into KPZ, you might tell me that, well, you didn't wait enough. You should really wait longer and longer to see where it goes. So on one hand, I have experimentally, we have the conflicting requirement that mu has to be smaller, which is experimentally challenging, and going to a larger t. So theorists would talk about it as two non-commuting limits too, meaning that you want to know what happens there, but the order of taking the limits matter. And so if you got to figure out a way to collapse your data, and this is the scaling we use to collapse the data. And in this case, after this, you come up with the scaling function, then the two non-commuting limits would appear in a very two different ends of the plot, so you can really make your mind. So we do this scaling of the same data plotted in here, and you see a acceptable collapse of the data, meaning that this scaling is actually a sensible thing to do. And the two non-commuting limits appear very different. See, and this is the limit for which the KPZ has been conjectured. So you look at the data in this limit, and you probably agree with me that there is no chance for it to happen in this band of values. And the work of the cold atoms happen to be on that limit, and happens to be in the window. So they concluded it falls under this universality class, because, you know, it's just posing that window. But the finer analysis of data shows that their data is mainly on the limit that that there is no conjecture for it to, this is not the correct limit to be in. You should really check the conjecture in this limit. There is no point of checking the conjecture in this limit. Okay, so the skewness is disagreed. Sorry, what am I showing? Skewness for KPZ is this value, and the value we are finding is 0. So we are disagreeing with each other. There are two other models which says the same, that the skewness should be 0. We can verify them. That if these models make any sense, by going to kurtosis. And the NLFH model tells that kurtosis should be about 0.14. And we see again, after collapse, there is no chance to assume that kurtosis is 0.14. And the classical Landau-Lifshitz model predicts kurtosis asymptotically get to this, which we cannot rule it out. So probably the same dynamic can be seen there. So let me make it clear. The quantum field theory for what we are seeing and the model does not exist. The CLL, classical Landau-Lifshitz, is a different classical model written, and it just happened to show the same physics. So it's a slightly, is not the answer to the mystery. Still, lots of unknown questions would remain. But it's just a classical model written that shows the nice physics. So, oh, wow. I want to stop in here, and just to assure you, I can tell you that these two limits of mu going to 0, t going to infinity can be done many different ways. But no matter how you look at this problem, there is no KPZ. Well, there is one way that theory predicts that you should do it. Mainly, first you take mu to 0 first, and then you take tau. This is where the theory prediction is. But if you want to do other methods, either you run into conflict with existing other data or other methods. So there is no room for KPZ in this model, it seems. Let me stop in here, and I hope I have made a case that we are doing interesting non-equilibrium models, spin models, that that is challenging for classical computers to solve.
Thanks a lot, Pedram. So let me clap on behalf of the audience. Any questions?
What happened?
So maybe let me ask you one question just to understand a little bit more about the KPZ part of the discussion at the end.
Sure.
So first, just to kind of, I have seen there is a lot of activity, but I haven't followed closely everything. But just to understand, so the idea is that KPZ appears at the SU2 invariant point but it's sort of the universality associated with the finite temperature behavior, right? So there's a fixed point, I guess, at 0 temperature, which is just a usual magnet. But
yeah, this is the infinite temperature physics.
Right, infinite temperature, which should be any finite temperature, probably. Like the finite temperature behavior, I would imagine, flows sort of in RG sense to infinite temperature, right? Or is it strictly different?
Well, by that I mean you have to get mu. Part of the conjecture is that you have to get mu equals to mu going to 0. The conjecture is in the limit that mu
Infinite
goes to
temperature.
0.
I see. Mu is essentially, mu going to 0 is infinite temperature, essentially.
Yeah, that's what I'm saying. The other values of mu, I just don't know how to define temperature. That's what.
But just sort of at the level of the theoretical conjecture, if I have finite temperature XXC chain, will this sort of motion of the particles?
Well, first you have to be as SU2. You have to get this delta equals to 1, which we got by checking. So definitely you have to be at Heisenberg point, and the conjecture is infinite time. Well, the conjecture is never written, is never clear. But if I have to give them benefit of the doubt, is that at the long time, when mu goes to 0, these two things should look like. And when mu goes to 0 or is 0, then I can define a temperature, right? When it's not 0, I just don't know, what should I call it? Two cold and hot things next to each other. I don't know what to. It's just, I don't want to use the word temperature away from equals to 0. But I do, maybe I don't know the answer to you that if this domain wall is finite, what would you see? I don't know. I don't know. I think you have to take the limit of mu equals to 0. If you really want to give benefit of the doubt to.
But even if you just do mu 0, I guess that's, how do you even tell what is the wall? Because that would look like you're at the infinite temperature.
Yeah, so that's the challenge. That's the challenge, that you cannot go absolute 0, so you have to extrapolate the level of mu.
I see.
Yeah.
I see.
And that's where the whole business of which limit to get first, because the dynamic gets slowed. So now, which limit you want to get first is a major headache. And then you realize these two are non-commuting limits, so collapse would just leads to them appear in a very different size. So, because from the later on the left, right, anyone can say, well, you give it enough time, it's just going to come to that window.
Right.
Yeah, that's
okay. So I seem to recall, I mean, I'm maybe just misremembering, but somehow this had to do with the diffusion of a spin, right? So spin diffusion would be kind of a naive expectation from from very naive hydrodynamics, but the idea is that the spin is not, is behaving, spreading, I guess, faster, right, than diffusively.
Yes, that's.
But so the statement is not just about this particular preparation in a domain wall. That's just a sort of convenient, sort of specific protocol to test this hypothesis of how a spin is diffusing, right? Is that true, or?
Let me see what you're. Well, the mean value, the propagation, is when delta equals to 1, which is the orange line, is super diffusing, right? Yes. This is the infamous 2/3.
Right.
And I'm showing you that, even when you lower the value of mu, so I'm refusing to define temperature for these high values of mu. These are high values of mu, and I'm telling, or I'm asking you to believe me, that if mu goes to 0, you can see the slope of these lines are not changing. They're just getting more,
Yeah.
they're showing more of the same. So
Right.
there is super diffusion. And then there is a scaling factor, which again, numerical work goes with KPZ scaling. So what more does it take to be KPZ?
Mm.
And then they make the conjecture. And now we are seeing that, well, is an interesting case that higher moments are telling you very different physics.
Mm-hmm.
Yeah.
Mm-hmm. I see. So it's maybe not KPC strictly speaking. It's sort of KPC-like in some sense.
Yeah, right. But it's a bit of, then it gets very philosophical.
Yeah.
All
Whether,
these things that we
whether
know.
this is
So
universal in a sense, what you're seeing in a sense. That's the question, right?
yeah, right. We have an instance of a case that something up to second moment was all kosher, and now all of a sudden doesn't work.
Mm-hmm.
So what if we go and check our all beloved cases that we know so far, how many moments they're gonna survive?
Right.
And what is the criteria? If it stops at 12th moment, what I'm gonna say?
Right.
So
Maybe there's a finer notion of universality, which you have classes that would fall into the different moments will fall into different universality classes, even though the leading moment, so to say, is KPC.
Exactly. Yeah.
That's very interesting.
Mm-hmm.
Any questions? So guys, please take advantage. We have here the expert of the world on this. So let me maybe ask you a kind of annoying question, okay?
Sure.
So is the quantum computer, is your quantum computer at the level in which these simulations cannot be done just with good numerics?
No, it can be done.
Right.
So the first experiment I showed you was done probably on a laptop. It was 24 qubits, or was it 24 qubits? Yeah, that can be done in a laptop.
Right.
The second one was 46 qubits. So we could do it in a university cluster. And if you spend a few months, you might be able to fit the wave function into a memory you have in your laptop. Yeah. But is an annoying game because well, one is the physics. One case, no matter how much hard you try with eventually someone can add 5 more qubits, and the physics goes totally out of your control in your laptop mapping. So that's the essence of it. Yeah. But on the other hand, you never know if a particular question asked, like this transfer magnetization. Let me show you something maybe. Do you see my screen?
Yeah.
Okay. So for instance, in this transfer magnetization, like this is the numerical page of it. You realize we are asking about this specific question of transfer magnetization. The numbers at cycle 2, at cycle 1, is a local question. So only these 2 qubits matter. What happens at the end of the chain doesn't matter. That's why this example, because we are asking this funny question, you can truncate the shape, the length of the chain at early cycles. There is a causal light cone that you can just totally live without, live within that light cone. So you see that the student was super clever, that even for like very short cycles, he wrote analytical forms, because this is a 2 qubit example, and the next one is a few qubit chain. You can truncate and you can rewrite analytical value for all the higher moments, all the moments. And then he could do exact density matrix, because again, when you're going at cycle number 8, a chain of 16 qubits sets your physics. And then he could go to whatever he's explaining in here is beyond me. GPU, NVIDIA. Okay, Google was not nice to him or something, I don't know. And if he could work a little harder, he could extend to this limit, but we just didn't do. But the point is that at this point, with a little grain of salt, hardware is as good or as challenging as numerical methods. Maybe you get a very good numerical person can do this much for you, but then we can add a few more qubits, and then again we get the advantage. So it's a dangerous game, but yeah, it's not beyond classical. It's just a student with few days of effort, he could go all the way to here very easily.
So, but then are you in a situation already in which, or how far are you from a situation, from the regimes in which, we cannot simulate this anymore in some reliable way with sort of usual classical?
Yeah, right. Right. You might say, so when we did this, I was very proud, and I went to our expert. I say, well, they told me go to the expert in the team, and he can do. He said 1D physics. 1D physics is known. 1D physics is simple, and he said he can do it maybe 1 million times faster. So let me see. This is 46 qubits, right? And then depth 23. This is more or less similar to quantum supremacy, where supercomputer fall apart. And then they say, oh, this is 1D. And the guy told me 1D problem are 1 million times, or maybe 10 million times simpler than 2D problems. Oh my God, 10 million times or 1 million times. But when you think about it, if you add 5 more qubits here, and then 5 more or 10 more qubits and depth 5, you catch up again.
Right.
So these huge things that numerical things can do, you can really overcome them. So if I want to be brave, I would say with good fidelities, as soon as you get to 70 qubits, someone could outperform you, but then you add 5 more qubits, and then you really outperform classical computer. But those methods are also improving. But the race is highly biased toward hardware implementation. I would say, yeah, 50 qubits, 70 qubits is very easily, it goes beyond what classical computers can do. And yeah.
So what is the time scale sort of where you would be in this very clear regime of, is it?
Well, I mean, depends on the problem. There's a paper we did on the measurement induced physics, which we use 70 qubits. So it depends on what you ask.
I see.
So you have to look at the observable you are interested in. And if you are lucky or not lucky, all of a sudden there is a solution for that problem. But I think maybe in 1 or 2 years, more problems would be safely in that size. I think, yeah.
Very good, very exciting.
Thank you.
Any questions from the people who have stuck around until now?
Thanks for your talk. Actually, I have a naive question to ask. From your talk, I can kind of feel that this 1D and driven system are very suitable for this chip to solve. So, I mean, in general, what kind of problem are more suitable for this quantum chip to deal with?
Spin dynamics, I think, is every time I go and shop around, I come back with the spin dynamics problem. I think these are you're truncating to 2 levels, and you're saying, was this excited or not excited on that lattice site? So I think, and the spin models are very good match. You can think a little more clever and maybe do a spin 1/2 problems. A spin 1 problems is not, use 3 qubits to define, use 2 qubits, sorry, to define a spin 1 or that kind of thing. But I would say XXZ model in 2D is as easy as this 1D problem. For us, it doesn't matter 1D or 2D. This example, because started from a theoretical prediction, and theories are heavily rooted in 1D physics. That's why these examples happen to be 1D physics. Otherwise, for us, we can just do 2D physics. So I think spin models is a very low-hanging fruit at the moment. Yeah.
Great, thank you.
Sure.
Okay, so maybe we should let you take a
Yeah.
break since you have had a very intense afternoon of talks.
Yeah. Thank you. Thanks, guys.
Thanks a lot.
That was great.